Winter, 1961. In a cramped office at the Massachusetts Institute of Technology, a meteorologist named Edward Lorenz is staring at a Royal McBee LGP-30 computer. It is a loud, cumbersome machine, roughly the size of a desk, possessing a memory of only 16 kilobytes. Lorenz is running a weather simulation, a simple model of atmospheric convection using 12 differential equations. He wants to see a sequence of data again, but to save time, he decides not to start from the beginning.
Instead, he inputs the initial conditions from a printout of the previous run. The original simulation calculated numbers to 6 decimal places, 0.506127, but the printout, to save space, truncated the data to just 3, 0.506. Lorenz assumes the difference, 1 part in 1,000, is inconsequential. It is roughly equivalent to a puff of wind hitting a weather vane. In the rigid world of classical physics, small inputs yield small variances.
He walks away to get coffee. When he returns an hour later, he expects the new run to duplicate the old one. Instead, he finds something terrifying. For the first few days of the simulation, the patterns align, but then they begin to separate, slowly at first, and then drastically. By the end of the run, the two weather systems bear absolutely no resemblance to each other. The tiny rounding error, less than the width of an atom in terms of atmospheric pressure, has completely erased the future. This moment marked the death of the clockwork universe. For centuries, since Isaac Newton, science operated under the assumption of linearity, that if you knew the position and speed of every particle in the universe, you could perfectly predict the future. This was the dream of Laplace's demon, an intellect that knew all forces and positions. Lorenz proved that in nonlinear systems, this is impossible. He had discovered sensitive dependence on initial conditions.
In 1963, Lorenz published his findings in a paper titled Deterministic Non-Periodic Flow. Yet the poetic name we know today didn't arrive until 1972. At a meeting of the American Association for the Advancement of Science. Lorenz intended to use a seagull as his metaphor, but a colleague suggested something more delicate. The talk was titled, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?"
Lorenz was not the first to glimpse this abyss. In the 1880s, French mathematician Henri Poincaré was competing for a prize offered by King Oscar II of Sweden to solve the three-body problem, predicting the movement of 3 celestial bodies orbiting each other. Poincaré discovered that while 2 bodies orbit in a predictable pattern, adding just one more introduces infinite complexity. The system becomes unstable. A tiny nudge sends the planets into wildly different orbits.
What Lorenz added to Poincaré's work was the visualization of this chaos. When he plotted the behavior of his weather equations over time, the trajectory didn't form a straight line, nor did it repeat in a loop. Instead, it traced a strange double spiral shape in 3-dimensional phase space. It never crossed itself, and it never repeated. This geometric structure, now known as the Lorenz Attractor, coincidentally and eerily resembles a butterfly.
This shape explains why your weather app is often wrong beyond a week. To predict the weather 10 days from now with perfect accuracy, we would need to know the temperature, pressure, and wind speed at every single point in the atmosphere with infinite precision. We would need sensors on every square inch of the planet, and even then, the heat from the sensors themselves would alter the conditions, rendering the prediction moot.
We must distinguish between randomness and chaos. Chaos is not random. It is deterministic. It follows strict laws of physics. If you could replicate the exact starting conditions of the universe down to the Planck length, the outcome would be the same. The problem is that we as observers cannot measure with infinite precision. We are limited by our tools, and ultimately by the uncertainty principles of quantum mechanics.
This leads us to the most common misconception about the butterfly effect, perpetuated by pop culture. Movies imply a direct, traceable chain of cause and effect, that the butterfly causes the hurricane. This implies agency. In reality, the butterfly is just one of trillions of variables. It is not the sole cause. It is the straw that breaks the camel's back in a system already teetering on critical instability.
Ray Bradbury's 1952 short story, A Sound of Thunder, predates Lorenz's paper,
but captures the public imagination of the concept. A time traveler steps on a prehistoric butterfly and returns to a future where language and politics have changed. While narratively compelling, chaos theory suggests something more subtle. The disturbance wouldn't necessarily result in a specific ironic twist of fate, but simply a divergent reality that becomes statistically unrecognizable over time.
The butterfly effect is deeply tied to the concept of fractals, geometry that repeats at different scales. Benoit Mandelbrot famously asked, "How long is the coast of Britain?" The answer depends on your ruler. As you measure with smaller and smaller units, the length of the coastline approaches infinity. This infinite complexity within a finite space is the playground of chaos. It is why we cannot brute force our way to perfect prediction. Chaos is not just an atmospheric anomaly, it is the rule of life. Your heart rate is not a perfect metronome. A healthy heart exhibits fractal variability. Perfectly regular heartbeats are actually a sign of impending heart failure. Ecosystems, stock markets, and neural networks all function on the edge of chaos. This instability allows for adaptability. If nature were perfectly linear and rigid, it could not evolve. Consider a game of billiards. If you ignore friction and assume perfect elasticity, how many collisions can you predict? It turns out, to predict the trajectory of the balls after just 1 minute of play, you would need to take into account the gravitational pull of every person standing in the room. To predict it after an hour, you would need to factor in the gravitational pull of a single electron at the edge of the known universe. This realization places a fundamental limit on the age of information. We often believe that with enough data and powerful enough AI, we can solve any problem. We believe we can optimize the economy or perfect society. But chaos theory stands as a mathematical wall. No amount of data storage can capture the infinite precision of the real world. The horizon of predictability is finite. Edward Lorenz died in 2008, but his legacy is one of the most profound shifts in human thought. He taught us humility. We are not masters of the universe, detached observers moving clockwork gears. We are embedded in the system, part of the turbulence. We cannot predict the ultimate impact of our actions, not because we lack the technology, but because the universe is fundamentally creative in its unfolding. The butterfly effect is often viewed with anxiety, the fear that a small mistake will ruin everything. But there is an optimistic inverse. It means that small actions have infinite potential. In a linear world, a small effort yields a small result. In a chaotic world, a single act of kindness, a new idea, or a moment of courage can cascade through the complex system of humanity and reshape the future in ways no model could ever predict.